All right. So today, what we have to get through is inverse dynamics. I think you have a pretty clear picture of what inverse dynamics is, as long as you studied something like Introduction to Robotics or Fundamental of Robotics, anything like that. Even theoretical mechanics in the robotics course might have covered this topic. I will discuss what it is, but before I do, I just want to point out that this topic, while in classical mechanics or robotics, it is introductory topic, basically is a simple enough task to identify, solve inverse dynamics problem. For robots with contact, until I would say the last decade, so during the early 2000s, maybe during 2000s, even early 2010s, this was the topic that people were trying to solve. So there were propositions, and quite numerous ones, on how to effectively deal with inverse dynamics for systems with constraints. So while it is not extremely new, this material is, I'll say, 15 years old on average. Yeah, it depends on which publications you go by. But this has been relatively recently what people were working on. So is in a sense you can see that this implies some novelty. This also implies that the material is not completely finished, right? You can imagine there could be some changes yet. And as we go on after this lecture, the material will be more and more so. Like it will be close and close in time to us. There will be less and less time that passed since it was proposed. There will be more and more research area. But this already, what I'm going to discuss here, is quite a research topic. All right. So let's look into it. To begin with, let us just understand what forward and inverse dynamics is. All right, let's do it. So let us consider a second order dynamical system of this type. Okay, Q double dot equals to some function of state variables, so Q and Q dot, right? State variables, and control U. Okay. Now, forward dynamics for this case is a task of finding Q double dot, right? Q double dot, given state variables and control input, right? So basically, here it is just compute Q double dot by evaluating the dynamical function. So it is quite obvious what it is. So it doesn't appear very hard to deal with. Okay, forward dynamics. Find higher order derivative for the system. Okay. So inverse dynamics, on the other hand, so sorry about that. So we have a inverse dynamics. Okay, inverse dynamics. For system G is a problem of finding control input, right? So now we want to find control input given a state and desired value of accelerations. So if previously we were trying to find accelerations, highest order derivatives, given state and control input, now we find control input given state and desired value of second order derivatives. So this, I think, is doesn't look too difficult, right? In a sense, in one case you find one variable, in another case another variable. Those problems become even more similar when you remember that both second order derivatives and control inputs are usually, not always, but usually linear, like appear in the equations in a linear fashion. So this makes it quite simple. And we're very thankful that we don't have to find state variables, which are actually highly nonlinear. So those guys, it will be difficult to find them. But second-order derivatives and control inputs should be easy enough. All right. Okay. Now, one second. Next, what we can do is consider where we get this desired value of second-order derivatives. That is not quite clear yet. So let's think about it. There is quite a connection between that and what we call a trajectory of a system. All right. So let's understand this. So let Q star be trajectory of the system G. Okay. What it means is that we could substitute this time function as Q into the system G, into its dynamical equation, differential equations. And we could find such control law, U star, that the system differential equations will become equalities, right? So differential equations will become equalities if we substitute Q, right? So Q star is a solution to the system, but this statement is qualified with the fact that, of course, the system also has input. So you cannot say that something is a solution unless you know what input is. So what we are saying is it is a solution for a particular input, right? We don't necessarily have to specify this input, even though finding this input is often kind of part of trajectory planning, right? But at least we want to say that there exists input that would drive us along this solution. So this is what we call trajectory, okay? We use quite a few terms in robotics. One is path. Path is a trajectory without time, so it is a purely geometrical expression. How the what parts of the state space the robot goes through and in which order, that is a path. And trajectory is the same but with time. So we go how fast we go along a path, that is a trajectory. Solution to ODE implies that is a solution to ODE, like a particular solution, a homogeneous solution, etc. Those kind of things. Those are all separate ones. By the way, I apologize. Something is up with my camera, and we might have trouble today. So I apologize. We'll try to keep it on. But... Okay. All right. So this is what we call a trajectory. I hope this is understandable. If this is not clear, ask me questions. I will be happy to explain. Okay. So far we think this is a solution for a particular value of U star, right? So a solution for a particular value of U star. Okay. Now, such trajectory, we can call it a nominal trajectory. Okay, nominal trajectory. And the control law U star, which supports this trajectory, we can call it a nominal control law. Okay, so nominal control law. Nominal here implies that the system could have many trajectories. And in particular, you can imagine if, let's say, there is a trajectory, right? Like there is a trajectory of some kind. I'm trying to draw it. But let's say your current state is somewhere a little bit away from this trajectory. You are here. That means you don't follow this nominal trajectory, right? You are already away from it. So the trajectory that you're going to take is a little bit away from this trajectory. But we still want to think about this nominal trajectory, right? We still want to, we still want to use it as an idea, right? This nominal trajectory. So this somehow implies that we want a different terminology, like whatever we are following, like our trajectory, that it may be going to approach the nominal trajectory. is, you could call it like actual trajectory, you know, whatever. And then there is a nominal one, which we will still going to refer to. So that's the idea. Nominal trajectory is just a very convenient way to refer to this, you know, to this one trajectory that we used, for example, in inverse dynamics, right? Well, you could have also actual trajectories and other types of trajectories. Okay, good. Now, let's move on. Let's say you have a point of time t of t. Let me just. All right. So let's consider this point of time t equals t1. So to this point of time, we have corresponding value of q of t, right? So it will be q1. And if we find derivative of q of t, it will be q dot of t. It also has a correspondence to t1, right? So position on the trajectory is known, velocity along the trajectory is known. Okay. So we get it by this expression. This expression. Good. So particular state, we can recover it from a trajectory. But what is interesting, not only particular state, but even acceleration we can recover from trajectory. We just differentiate the trajectory twice with respect to time, and then we evaluate what we get at t1. So notice, this is a perfect recipe for inverse dynamics, right? Here is the state variables, right? State variables. Here is a desired acceleration. Notice that here, like, since you know where we got them from, you feel like it is more natural to refer to them as a trajectory. It's first-time derivative, it's second-time derivative, right? That feels more natural. But for inverse dynamics purposes, this you can say is a state variable. This you can say is a desired acceleration, right? We got it from a trajectory, but well, first we didn't have to. We could have gotten it elsewhere. And second, for inverse dynamics, it is not very important where you got it from, since inverse dynamics is not like doesn't have to be depend on trajectory generation. So I suggest simply as a way of discussing it, like as a verbal convention, it is good to use both designators. Like it is nice to remember that this guy is a trajectory, and all of those are just derivatives of the trajectory. So this is useful. You will remember where you get them from. But it is also nice to use this inverse dynamics language of this as being desired acceleration, and this being a state for which you solve inverse dynamics problem. All right. Okay. Sometimes, and this is like a very gray territory. This is a very gray territory. Like you have to be very careful about it. But sometimes, instead of using state from a trajectory, people are tempted to use current state of the system. So actual state that you get from sensors or that you get from something else. Okay, so this happens sometimes. Okay. Also, something that again you have to be very careful about is you would say, okay, desired acceleration is good, but I want not the acceleration from the trajectory, right? Not the acceleration that I get by differentiating trajectory twice, but I want this acceleration plus PD control. So what I'm trying to say is I'm a little bit away from the trajectory. So here's my current trajectory, and I'm a little bit away from it, right? I'm here. So what I want is not to follow this trajectory from this point, so move in this direction. Instead, what I want is to land on the trajectory. So I want to go in this direction. So to my desired acceleration, I add a PD controller that minimizes the error between me and the trajectory. Okay. And then you would be solving the inverse dynamics for some kind of state, which can be your current state or your desired state on the trajectory, right? And additionally to that, you would use here not second derivative of the trajectory, but you would use second derivative plus PD control. So PD control will tell you the accelerations that you need to achieve in order to minimize the error between it and its trajectory. If this point is unclear, or if you want more information, you have two options. One is you can ask me, I will give you information about it. Or second, you can read the chapter on Lyapunov analysis and PD control for nonlinear robots in any introductory robotics textbooks. You would see their treatment of this problem. All right. It is profitable indeed to make a difference between terminology you use for inverse dynamics and trajectory. But trajectory is a source for inverse dynamics very often. Okay, I hope I made this somewhat clear. All right, so if you know this from the trajectory and this from the trajectory, you can find nominal control law by solving inverse dynamics, okay? And this is very typical. This is a very typical exercise. Well, let's see how it's done. Before that, though, just a few more words. I apologize. First, we have a lot of theories, and then we'll have practice. All of this is true for systems with and without explicit constraints. Like what I was talking about is true for normal systems and for systems with constraints. Why? Well, because systems with constraints, like explicit constraints, for them the problem is exactly the same, because constraints themselves, as I showed you in the last two lectures, can be expressed as functions of the state and input, control input. Okay, so you can compute the value of constraint of the reaction forces in terms of state variable and u. Or if you want, you could compute them in terms of second order derivatives and state variables. All right. So this implies that you could still pose exact same problems. You would just have those additional variables sitting around, but they're not changing anything in what I said. The idea of a trajectory is the same, right? Still Q star with a control law U star, nominal trajectory, nominal control law. The fact that you have reaction forces does not change anything here. They exist, right, explicitly, but they don't change the fact that you still, you're still trying to find U star, you still try to find Q star, right? Okay. And all of this is quite closely related to the fact that you can transform differential algebra equation into ordinary differential equation by excluding algebraic variables, okay? The fact that you can exclude them is more or less directly relevant here. Because since you can exclude them, you don't have to talk about them when you formulate the problem. Okay. All of this is true for the types of systems that we saw before. Okay. Now, some observations before we move on. Maybe this should be at the end of the slide, I don't know, but let's make some observations. So given the system G with n generalized coordinates and m control inputs and k independent constraints, we can find three different scenarios. Okay. First scenario, system can be underactuated. What does it mean? It means that not every acceleration is available. So there are some generalized accelerations that are not available. And I'm not talking about the generalized accelerations that are not possible because of the constraints. I'm talking the accelerations that are not, should be possible, but they're not available because you don't have control authority. Just to give you an obvious example of underactuated system, if you have a rigid body falling in the field of gravity without any motors, there is only one acceleration that's available. That is the acceleration that has to do with gravitational force. Acceleration sideways should be possible for a rigid body, right? Same as rotations and so on. But they are not available because you don't have motors, right? You don't have motors. Quadrotor cannot go sideways. Like it has to first tilt, then go, okay? So quadrotor has only 4 accelerations available at any moment of time. Whereas, so it's underactivated, okay? There are quite a lot of those underactivated systems. Acrobot, Pendobot, those are famous examples of underactivated systems. Right, so when does it happen? This happens when number of degrees of freedom of the system is higher than the sum of constraints and control inputs. Okay. It's higher than the sum of constraints and control inputs. You can imagine, like, this might sound to you a little bit esoteric, okay? So why does this, why do those numbers matter? Well, to make it a little bit more clean, think about a robot arm, okay? Imagine KUKA, robot arm. It has exact same number of degrees of freedom as it has number of control inputs. That is a fully activated robot, all right? Fully activated robot. On the other hand, imagine a quadrotor. Quadrotor has 6 degrees of freedom, but only 4 motors. It is underactivated. All of them have 0 constraints. All of them have 0 constraints. Okay, good. Good. What about constraints, though? Why does it? What I just said, I think illustrates why this equality would be true. Like n bigger than m means underactivated, right? Where do constraints come in? Well, a walking robot, for example, you can imagine, is without constraints. It would be just like sitting in space, like you can imagine a human body. I will just quickly draw it. Okay. Humanoid body. Okay. It just sits in space. If it doesn't have a ground to sit on, it would simply have 6 degrees of underactuation. The center of mass couldn't change its like acceleration. The center of mass has to be 0. And rate of change of angular velocity, I mean, I'm oversimplifying here, but let's say rate of change of angular velocity has to be 0. Again, I'm oversimplifying because there is a 3D rotations are a little bit more complicated than that. But yeah, okay. Good, but put it on the ground, put this robot on the ground, if you have a ground under its feet. And then, because of reaction forces, it can actually change rotation, orientation of the center of mass. It can change position of the center of mass. So somehow the underactuation goes away. All right, and to describe this situation in terms of actual variables, what we have is this. So control, you have control inputs and you have independent constraints. Their sum has to be, if it is still less than n, you will still have underactuation. This is not a law. This is more of a quick rough test, because there is a possibility of linear dependence between the action of constraints and the action of control, like torques, internal torques. We will see all of this in a bit. But this is a useful thing to just imagine in your head. All right. Second scenario. System is fully actuated. Fully actuated, it means that usually that you have same number of degrees of freedom as the sum of number of motors and number of constraints. Okay. So for a walking robot, what you would often have is 6 linearly independent constraints, even when one of the legs is being lifted off the ground. So imagine one of the legs is lifted off the ground. The other one would have 6 linearly independent constraints, and the whole robot would have exact same number of degrees of freedom as number of motors plus number of constraints. Right? That is the possible scenario. Fully activated. Right? Fully activated is like KUKA robot. Now, a system can be overactivated, over-constrained, over-redundant, etc. That is when you have less degrees of freedom than the sum of motors and constraints. This would happen if you have, for example, both legs on the ground. They'll be overactivated. Correct. Right, over-constrained if you want. Right. In general, this is a very typical scenario. This is a very typical scenario. Yeah. Like parallel mechanisms, you can think of them as being overactivated or over-constrained if you think of them as having constraints. Okay, so this is just something to think about. Now I think the theory is over. Let's see the mathematics. Right. I think now we will be in a cleaner water. All this, like trying to do robotics in terms of words is always difficult. I think in terms of numbers and formulas is much simpler and more understandable. Okay, so last lecture, you remember what we saw was this system, right? So it is some projector times this classical equation, like manipulate equation, right? All of this equal to 0. Okay, and you remember that this projector looked like this. This was a Schur projector, what we call it, Schur projector. Now let's open H, and I open H in this form. Okay. Last time the way I opened H was with tau here. So here it was tau, not TU. Tau was generalized, external generalized forces. Now TU is some matrix, control map, I call it. And U are motor torques. This is a typical way we describe them. It is just that for manipulators, T is often identity, okay? But for working robots, T is often identity and 0. So it is a rank deficient matrix. It is, in fact, usually tall matrix. So T doesn't, but for manipulators, it will be full rank identity matrix. Okay, all right. So this equation 1, becomes equation 2 here. It becomes equation 2 here. Right. Now let us consider this system. But now notice what I do is I replace generalized accelerations with desired generalized accelerations. Okay. So what we have before? What we have before? But now we have desired generalized accelerations here. Right. Now, how do we solve this? How do we solve this? Oh, actually, this is laughably simple. The way we solve it is just using pseudo inverse. So we have a matrix in front of you, and we have a vector here. Okay? So we have a vector, and the matrix should be pseudo inverted. That's it. That is how we solve it. So all of these discussions before, all of this talk about trajectories, how to call them, all of this discussion of underactivated, overactivated, etc., is nice and important, but the mathematics itself is maybe not clear, right? It's maybe difficult to understand. But the mathematics itself here, like at least this part of mathematics, which is actual solution of the system, is extremely simple, extremely clean. All right. Good. 1 second. Okay. So what we saw was this system is like this inverse dynamics problem. So what we were discussing before That was it. And the solution is quite simple. Okay, let's see. Let's see if there is. Yes.
Sorry, Professor. In the question 3, the Q double dot star should.
Yeah, Q dot star. Yes. This is the same as this one. So yeah, the star is missing. Should be the same. Yes. By the way, if any of you want, you can submit the fixes to the lectures in the GitHub. Up to you. I will of course fix them myself as soon as I remember. But if you want to submit fixes, I'll be happy. Okay. Let's see what we have. What else we have? Of course, since it is pseudo-inverse, it's not analytical inverse. We don't have a guarantee that the solution will be exact, right? In fact, what I would like to say is, this is pseudo-inverse is a least square solution to the least square problem. So on one hand, it provides us the solution with the smallest norm, right? And on the other hand, with the smallest residual. Okay. Smallest norm is perfectly good for us. We are happy with the smallest norm. Smallest residual, though, implies that residual doesn't have to be 0. And if the residual is not 0, it implies that it is not actually a solution to the inverse dynamics, because then we would substitute the solution back into the original equation if we are not going to get the accelerations that we wanted. So the equation of residual is quite open for us. So while this looks nice, it doesn't have to be provide us a solution to the inverse dynamics. So we could rewrite this. Provide a criteria when the solution actually exists. So we can substitute this expression back into the original dynamics. Okay. So here's the original dynamics. If we substitute pseudo-inverse, so let me just show. This is the original dynamics. Okay, here it is. And pseudo-inverse that we substitute is this guy, right? Okay. This has to be equality. If this is equality, like strict equality, then we found the solution. If this is not a strict equality, if this equality is somehow like doesn't hold, then what we found was a solution with the residual, right? And this is not what we want. So let's try to see what would be the condition. The way we could see this is by taking this out of the brackets, like this and this. Okay. So transfer the right-hand side to the left. And we get, let me use glue to notify. So we get this out of the brackets too, right? So this goes out of the brackets. This goes out of the brackets. And finally, we have this expression and identity here to form this guy. Okay. So we have, like, when we put everything to the left-hand side, we get I minus this x whole expression with the PS, with the green, this like, what do you call it, manipulator equations, I guess, here. Okay, so this is how I rearranged equation 4 into equation 5. I think it is quite clean what I did, right? Like substitute U, express this green component that looks like manipulate equation, got my projector that I had previously. And then this red part is what we got from inverse dynamics. All right. Now, what we can see here is that here is a matrix. Here is the matrix pseudo-inverted. Okay, so this matrix is pseudo-inverted. Okay, this is a classical form of a column space projector. Okay, this is a classical form of a column space projector. Now, for this matrix PST. Now this I minus column space projector together forms a left null space projector. So this is a projector, and orthogonal projector, not just any projector. Like PS is a projector too, right? But this guy is orthogonal projector. Okay, so they have special properties. So this is orthogonal projector to the left null space, and we are saying that this guy times this projector to the left null space of this matrix. All of this has to be equal to 0. So what we are trying to say actually is that this matrix, so manipulate equations times the Schur projector, should lie in the column space of PST. Why do I say it should lie in the column space? Well, because if the whole space is divided into orthogonal, can be divided into orthogonal parts, okay? Left null space and column space, they form, they are orthogonal complement of each other. Together they form the whole space. Row space and null space, again, orthogonal complement of each other, they form together the whole space, okay? So if a vector has 0 projection onto one of those orthogonal complements, then it lies entirely in the second one. So if something has 0 projection on the null space, it would lie entirely in the column space. Oh, sorry, in the row space. If something has no component in the column space, it lies entirely in the left null space. Okay, most vectors would lie in both spaces, of course, right? But if this is true, equation 5 is true, it means that these green vectors, they show here. Let me use consistent notation. This green vector lies entirely in the column space of this matrix. And notice that this green vector is actually just left-hand side of the equation that you got, right? And what is the column space? Well, column space of this matrix. Let me use orange. So this orange matrix is actually makes sense. It is just the control matrix. And yeah, of course, the left-hand side should lie in the column space of the control matrix. Otherwise, you're not going to get anything. So while manipulations that we did here, they are quite large in terms of number of symbols, but what we got is completely obvious result. We wouldn't expect a solution to exist if we are trying to find such U that produces a vector here, which does not lie in the column space, entirely lie in the column space of the matrix to which U is multiplied. Of course, that's just obvious, right? That's obvious from the definition of what it means to be in the column space or left null space, right? If part of this vector lies in the left null space of this matrix, the definition of what it means to be in the left null space is that it cannot be produced. So in a sense, it is directly implied that you wouldn't be able to find such U that produces it. Okay. All right. So this is the criteria. And for us, it is quite important to keep it in mind because it is more than easy to, when you actually work on something, to start asking for difficult accelerations. Then you get results, and then you accumulate error. And you don't know the source of error. And you wouldn't know the source of error if you don't check, for example, such conditions, right? So it's very important to check if what you are asking for is actually feasible. Okay. Is it clear? Any questions regarding that? Okay. If no questions, I'll move on. Now, there is a very nice theorem that is proven in this paper. Okay. Very nice theorem proven in this paper. The theorem goes like this. If you have two projectors, P1 and P2, which describes the same dynamics in this form. Okay, so let me use a different. That describes same dynamics, but in this form, right? One describes dynamics as P1 times manipulate equations equal P1 times TU. Second is P2 manipulate equations equals to P2 TU. Okay, so you have same dynamical system. By same dynamical system, I mean there is the same relation between the higher derivatives, control input, and so on and so forth. So the solutions will be exactly the same from the same initial conditions. Just the form is different. So if there exist two such projectors, the following is true. The inverse dynamic solution to the given the first system would be equal to the inverse dynamic solution given the second system. So as long as your projectors describe the same dynamics, doesn't matter which one you use, your inverse dynamic solution will be exactly the same. Okay. So remember last time we had Schurk projector and we have QR decomposition projector. If they indeed describe the same dynamical system, you could use this fact to apply them interchangeably in your inverse dynamics problems. So you don't have to worry which one produces more advantageous inverse dynamics, Schur or QR. Doesn't matter, they're actually exactly the same. That is quite interesting. Quite interesting. They have even stronger result in the paper. Yeah, I advise you to read it. They prove that weighted inverse will be the same, not just the inverse will be the same. The weighted inverse will be the same. So even stronger result. Okay. So what we have here is basically a description that you could use any of those projectors. Yeah, nice. Is very good. Very good. Now, but before we move on, let me remind you of what weighted inverse is, weighted inverse is. So here I will show you two ways to derive a weighted inverse. By the way, why do we need weighted inverse? Oh, because you notice here what we did actually is just use a pseudo-inverse, right? Here we did the pseudo-inverse. This is not the only way to invert stuff. So I will now show you two more ways. I mean, it will be roughly the same thing, but two more ways. And then we could see how it is useful in terms of inverse dynamics. Okay, so weighted inverse. So weighted pseudo-inverse problem is a problem of minimizing this difference, like ax minus b, which obviously is related to the equation ax equal to b, right? So this equation is somehow relevant to here, right? So we minimize residual. Ax minus b is a residual of this equation, right? A residual of this equation. What I mean by residual, just in case you don't know, residual is ax minus b. We just say what is the if the equation is not equality, like it doesn't have a solution, what is the residual? So we want to minimize the residual here. But we don't just minimize the residual. What we minimize is a norm of the residual with a weight. Well, what is a weighted norm? Well, weighted norm is like a norm, you remember, is a square root of a dot product with itself, right? So you take a dot product of your vector with itself, take a square root. That's a norm. Well, weighted norm has a matrix inside the square root. So rather than it being a dot product with itself, it is a quadratic form with this weighted matrix. So this is a matrix of coefficients. And what we have here is what we have here is the what we call weighted norm, right? This matrix can be, for example, if you mention diagonal, and if it is diagonal, you could say that each element of diagonal determines the weight of this component of X, right? So the result would be, for example, if V is something like, let's say, 2, 0, let's say 0, 1, right? Then your weighted norm of X, some omega, sub W, would be 2x squared plus, 2x1 squared plus x2 squared. Okay. So this is how you can use it. You can say, okay, we care about the first component twice as much as about the second component. And of course, it can be any positive definite matrix. This is what I mean by W bigger than 0. I mean it is positive definite. So I don't mean it is positive element-wise. I mean it is positive definite. Positive definite means that quadratic forms are always positive or 0 only at 0. Okay. So this is the definition. So this problem can be equivalently rewritten in this fashion. How did I get here? Well, first of all, you can get rid of the this square root, because the square root of a scalar has a minimum that corresponds to the minimum of the scalar. Like if your cos function is a scalar under a square root, the minimum of this function will be achieved in the exact same place as the minimum of the scale itself. So you don't have to independently provide, you don't have to discuss the square root of the function. You can directly discuss the expression under the square root. Okay, this is not applicable to, for example, sum of two square roots. Okay, it's only applicable when you have a single square root in the problem. Okay, so I can just discuss x omega x, and that's what I do here, right? This is my x. So let me. Sure. My x is this guy, right? So here it is. My x is this guy, so here it is. Okay. But what about omega? Well, omega, the W, I break it as a sum of two matrix square roots. So by definition, what is a matrix square root? That is a matrix which you multiply by itself to get the original matrix. Okay. So square root of matrix is the same as square root of anything else. You multiply of a number. Okay. You multiply it by itself and you get the original. And this is what it is. It is defined only for positive definite matrices. Positive semi-definite you could do too. For negative definite matrices, you can imagine why you cannot do this. And by the way, if some of you know, you can tell me. Is something. Maybe I should give it as a as a challenge, of like bonus point challenge if you want. Like, why is this? But this is, I think, you can just look up in Wikipedia, so it wouldn't be as interesting. But if you can prove, if you write me a proof, then yeah, I guess let's make it a bonus point challenge. If you can prove that square root is not defined for matrices which are not positive semi-definite, then that will be a bonus point challenge. Good. But they only defined for positive definite point matrices square root. And as definitions, again, you multiply by itself, you get the additional matrix. Nice. Now, the next stage is to redefine. Write this equality. How should I put it? We notice that this is the same as looking at this matrix times this matrix, or this vector times this vector. Okay. which is equivalent, like this is equivalent if you consider one of them, if you consider both of them. This is equivalent to solving least square problem of this type, okay? So what we wrote here is a least square problem, just for new variables. So now you have a new B, like a new right-hand side, and you have a new matrix. Well, why is it equivalent? Like, let's say we want to solve this problem here as a least squares. What do we do? Well, we want to minimize norm of the residual. Norm of the residual would be, like the residual would be this expression. Like this is the residual for this expression. And over this overall thing, let me show it. Like this overall thing is minimization of the norm of the residual. Because again, we can ditch square root that appears in the norm. So what we get is just a dot product of the residual with itself. That's what we minimize here. I think that what I just said might not necessarily be completely clear because we use a lot of ideas, right? We use square roots, we get ditch the square, we ditch them, decompose matrices and so on. But so if you have questions, please ask me right now or later, like anytime. I'll be happy to explain them. I just don't want to belabor a point that some of you get, so it would be boring, you know, if I repeat the same thing again and again. But yeah, so this matrix, you can notice this matrix is essentially an expression of the residual of this for this equation. So this is the residual of this equation. Again, residual is you get left-hand side minus right-hand side. That's the residual. That's what it is. And if it is a residual, right? This is also a residual, just transposed. A residual transposed multiply. You know, this multiplication gives you a dot product of residual with itself. Minimizing dot product of a residual with itself is the same as minimizing the norm of the residual. So this is in fact a least square problem for this system. But we know the solution to the least square problem. The solution to the least square problem is always Moore-Penrose pseudo-inverse. So we have to pseudo-inverse this matrix, multiply it right-hand side by it. So we pseudo-invert this matrix and multiply right-hand side by it. Okay. That's it. That's it. So weighted pseudo-inverse looks like this. We still pseudo-inverse, just we have the weighted, the weights, these weights appear here and here. Okay. I would really like to double, triple check those things. It's easy to make a mistake because we did quite a few steps. Yeah. Okay. So if you have questions, let's hear them. Okay, no questions. Okay, good. I will assume that you understand. This is not crazy stuff, so I'm not surprised if you got it on the first try. Yeah. Okay. Well, now let's consider another type of weighted pseudo-inverse problem. This time I write it in a different fashion. I say minimize x omega x, so minimize the quadratic form, subject to linear constraints of this fashion. Okay. This, some of you may recognize as a bonus point from the bonus question from the last lecture. I asked you to solve it, and 2 of your colleagues submitted solutions. So it was very nice. And the solutions were very, very pretty. So Okay, so how do we solve it? We solve it with Lagrange multipliers. The way we do it is we say, okay, this constraint can go into the cost function, multiplied by a Lagrange unknown coefficients, here Lagrange multipliers. They multiply this a minus xp, ax minus b, sorry. Yeah, and that's it. So again, let me just point out. Original cost stay the same. Constraint equations get into the cost, and we have additionally Lagrange multipliers. Okay, and so you get this new Lagrange function, Lagrangian. Okay. Next, what you do is you find that partial derivative with respect to x and partial derivative with respect to lambda should be equal to 0, right? That is a classical condition for optimality, right? First order condition for optimality. You notice that the partial derivative for Lagrangian function with respect to multipliers is actually this, right? This is what it is. And this should be equal to 0. Okay. So, yep. So basically we recover original constraints, right? Our constraints are recovered by this partial differentiation. Okay. Now, what we do next is we find dl dx. dl dx is this guy. Why did we get it? Well, we differentiate the cost, right? This comes from the cost, original cost. And this comes from differentiating Lagrange multipliers times constraint. So lambda times a is from here. Basically, this is where we get it. Right, then we transpose it and express x out. We get this nice expression here. 1/2. So the expression for x is x is equal to 1/2 omega, like W inverse, A transpose lambda. Okay. Now, next, we remember that constraints equations hold because of partial differentiation respect to lambda, right? So we can substitute x into this constraint equation. Let's see it. So we take this x and substitute into it this x, substitute into it this whole expression. So here's what we get, right? We get this 1/2 and W inverse A transpose lambda. From this, we can express lambda. How do we express lambda? Well, very easily. This we pseudo-invert. We get 2 and this pseudo-inverse. Okay, so this is just classical least square problem. I pseudo-invert it, but of course, if A is like a matrix which is wide with linearly independent rows, which is what we would expect it to be, right? If it is, for example, tall matrix, and the rows yeah. So why wide? Why? Because we usually you don't have, like, if A was, for example, 4-rank square matrix. If A was 4-rank square matrix, what would we have? We would have a single solution here. Okay, we would have a single solution here. This would make it irrelevant what the cost is. All right, fair enough, good enough. One solution. The problem only has one solution. If A on the other hand was, let's say, tall matrix, and it would have the rank of row rank of A would be equal to the number of elements on X. Again, there would be a solution, of course. but then you would have to ask like for solutions that minimizes the residual here. So it would be a solution with the residual. It's fine. It's very normal for least squares, but it is not something that we care about in inverse dynamics, for example, right? It's not something we care about in inverse dynamics, but that is completely normal for least squares. Okay, so it would have a residual, and then we would ask to minimize this guy here while minimizing residual at the same time. Okay, no problem. Now, the last scenario is when it is a wide matrix, then it would have a null space. So there is a null space in which we can actually minimize the cost function while having a zero residual. Okay, and this is the inverse dynamic situation where we have our constraints provide us in some room. This room is exactly where we define cost functions, but we do not have a residual. That is our situation. So if it is a tall wide matrix, then this expression is a wide matrix times tall matrix with something in between. That is usually invertible. Okay, especially if the rows are linearly independent for A, we can prove that it is invertible. So in fact, instead of pseudo-inverse here, you would have analytical inverse here. Okay, but you have to go through all those hoops to talk about it, right? You can't just assume that this guy is invertible. It would be invertible if A has linearly independent rows. That's when it would be invertible. You can prove it, by the way. It's quite doable to prove. There are even like theorems which will allow you to prove it in like in one line. If you know congruence transformation, then you can prove it in one line. Okay, so this would be invertible. And then you have here analytical inverse. Okay, last step. We take all of this and we substitute it into here. No, not into here, sorry. Into here. So we get this guy, right? And we get what we substituted, so this guy. And this is our final solution. This is our analytical pseudo-inverse derived by Lagrange multipliers. Okay. Good. This form, you already saw it before. This is something that we saw something that looked a lot like it in the last lecture. Okay, so both of those can be used to solve inverse dynamics, solve inverse dynamics. So, for example, consider this problem. Minimize this residual with respect to weight matrix. Well, the solution could be written this way. So here you have a control matrix. So what we would have called A matrix. Here we have a B, so right-hand side, right? So here is our B. Okay. Here is our control matrix. And we have addition to it those square roots, okay? 2 square roots that come from this weight matrix. Okay, so this is an example of how you can use all of this directly as applied to inverse dynamics. Do we have questions? Okay, no questions. Now, this you can basically find in the papers that I recommend you to read. Okay, last one for today. All of this was analytical ways to solve inverse dynamics. Now, in life, it is very often the case that you couldn't solve it analytically. And that has to do with inequality constraints that sometimes appear in inverse dynamics, which we are not going to touch today. We're not going to touch it today, okay? But sometimes they appear. And then what we have to do is solve it numerically. Right now, I will show you how we could solve it numerically for the stuff that we already discussed. I'm not going to argue through, like, say anything about inequalities. I'll just show you how we could solve the same problems that we solved using least squares, but in a different way. Okay. So what I mean in a different way? We could solve it using QP. And here it is, right? So here is our dynamics. We have this manipulator left-hand side. We have our control matrix. We have our constraints, reaction forces. Sorry, and this is our constraint equation. So what we could do is, for example, say find us the smallest possible u square. So norm of u, if you want, such that this expression holds. Notice that here we don't have any. We don't have the second equation. So this second equation is somehow lost here. Okay, doesn't appear. That is a sign that we should tell you that it is dangerous. What's going on is dangerous. Why? Well, because you lost some piece of information. It is not encoded in any kind of projector or anything like that. But still, if your acceleration is correct, this is the only thing that is constrained here. So as long as your acceleration is actually correct, it is no problem that you lost this information. It will be a problem if you propose incorrect acceleration here. Then it will be a problem. But if you're not, then everything is fine. Then the question is, so given this acceleration and given everything else, find such u that this holds. But notice decision variables are two. There are two decision variables. One is u, okay? So this is where u appears. Another one is lambda, okay? Here's where lambda appears. So you have two decision variables. And lambda, you don't ask it to minimize lambda, but you could ask it to minimize lambda. And lambda is a decision variable. So again, it is quite simple. And here you can notice another way to describe the availability of your accelerations. So since this matrix is full rank, there is one-to-one correspondence between this whole vector. Let me show between this whole vector and accelerations. So there is one-to-one correspondence. So there is for each of the vectors here, there is a unique acceleration. So we could just treat this whole thing as a vector of pseudo accelerations, if you want. Okay. Now, what you could say is, as long as this vector should span Rn. Okay, Rn. If you want to have accelerations in all accelerations in Rn. Of course, this is not true, right? Since this guy prevents you from actually using all accelerations in Rn. So what you should actually have is accelerations that live in Rn minus k, where k is the number of rows here, like as a row space size of this equation. So you already see, right? N minus k, something familiar. Okay. Now what you could say is, as long as this right-hand side can span the entire space here, everything is good. Okay. What do we mean? Well, we mean that this matrix C J transpose should have a span or column space that covers all of this. Okay. Of course, I'm simplifying a little bit, right? Because you also have this guy, but this is just a particular solution, you could say. This is a particular solution, you could say. Yeah, it's a single vector. It just shifts the space. Yeah. So this is the situation. This is the situation. You could check this if this matrix can produce all outputs in this space, and this you do by projections and so on. And if it does, then your system is fully actuated. Yeah. If there is a one-to-one correspondence between like a acceleration here and u and lambda here, then it is fully actuated, period. Okay. If there is a one acceleration that corresponds to multiple different u's and lambdas, then it is overactuated, okay? Overactuated or overconstrained. And finally, if there is a such u double dot which agree to this constrained equation, but cannot be reproduced by any variables here, then it is underactuated. Okay. Well, this is a more correct, I would say, way to discuss those things. Okay. Now, this may sound to you, I think you already know, this is a QP, so this is a quadratic program. Why is it a QP? Well, because this is a quadratic cost. This is a linear constraints, right? And to you, and you, just in case I would repeat this, I think you all know this already. This is done, solving this problem is done by solvers, so special software which solves convex problems or specific quadratic problems. For example, in MATLAB, it will be QuadProg, right? Yeah. There are specialized software such as Mosaic, Robi. Yeah, there are free software such as Sidumi. You can solve it even with SDET3, I think, if I remember correctly. So there are options, multiple options. There are languages for doing it, like, for example, CVX, which compatible with MATLAB and Python. So, if you somehow don't remember this, I recommend books on convex optimization by Stephen Boyd. I have also a course on it. So, okay, now you're familiar with this. I'm fairly sure. I'm just saying it just in case, so it won't hang in the air. Okay. To you, I think the more important question is not all of this, but rather, why would you bring this elephant into this tiny room, right? Why would you bring this QuadProg, which is a convex optimization, slow, huge, huge machinery, when you could do it as a pseudo-inverse? Pseudo-inverse is orders of magnitude faster because it uses a single SVD decomposition, whereas QuadProg uses multiple ones. Okay. Well, the reason is because later you would find that it is essential to use QuadProg in some certain situations. So there will be situations where this exact formulation, equation 20, is the only one available. And I wanted you to see it here in inverse dynamics, so that later when it becomes necessary, you could see the connection between this guy and the inverse dynamics we did before. Okay, so for now, we'll just see if it's possible. We'll see that it will be necessary later. Okay, now, as before, I recommend you read those two papers. This guy here is Yeah, this one is the one that I used quite extensively for this in the previous lecture. But this would contain a lot of the same material. So here you would see, you just see that like is the way it developed over time, but they explain some of the stuff more extensively in the second paper. So both of them are available on the internet. You can read them. I highly recommend. I highly recommend. There is entire body of about 10 papers in this whole field, like of orthogonal constraints, orthogonal decompositions. I don't say you should read all of them, but I want to say that it's possible to read all of them. This somehow implies that you could get expert level knowledge on the subject in a reasonable time, if you understand all of those papers. Saying it because it is not so often that you can get expert level knowledge on something in a reasonable time. So, okay. And I think this is it. Next time, we will take a break from the mechanical equations, which we looked at for, I believe, 3 weeks, right? 3 weeks. And next time, we will go towards linearization. So we will see how we can apply our knowledge here that we gained here. And remember what the knowledge we had from linear control to get to a very interesting, immensely practical, but also maybe a stage of abstraction further from simplicity techniques. So next time is a very important lecture. Don't miss it. It's very interesting too, and the stuff that I'm going to show you is going to be easy to apply. Okay. All right.
Thank you, Professor. Goodbye.
Yeah. Thank you. We'll see.
Thank you, Professor. Bye.